Now, whatever signal comes at the input side will have a frequency which will be varying from Fc towards Fc plus delta F and then towards Fc minus delta F. So input frequency will be varying over this range. So this is the variation in the input frequency. Now let us see what will happen on the output of the secondary side, because the vertical axis represents nothing but the amplitude gain offered by the bandpass filter. The plot on the y-axis will represent the output amplitude also. So let's say if Fc comes on the input side, it will generate this much corresponding output voltage. If Fc plus delta F comes on the input side, it will generate maximum output voltage as can be seen from the spectrum. And if minimum frequency enters on the input side, which is Fc minus delta F, then the output voltage will also be minimum. In general, at any given point of time, input frequency from this FM side will be anything between Fc minus delta F and Fc plus delta F. I repeat, delta F is the frequency deviation which represents the maximum value by which Fc will change on both the sides. Just to give you a better clarity in terms of numbers, let's say if Fc is equal to 10 megahertz, for example, and let's say delta F is equal to 0.1 megahertz, then the range of input frequencies will be Fc minus delta, that means 10 minus 0.1, which will be 9.9 megahertz, to 10 plus 0.1, which will be 10.1 megahertz. So all the input frequencies will be between this range. The center frequency will be the carrier frequency, which will produce some constant center output voltage, and maximum frequency of 10.1 megahertz will produce maximum output voltage. So let me mark y-axis as output voltage, which is nothing but gain also, because we are keeping input voltage constant, and in that case it's an FM signal, the input voltage is constant. In that case, the output voltage also represents the gain. They will have the same proportion. So 9.9 megahertz frequency will generate the smallest output. So the variations in the frequencies on the output side will be available in the form of variation in amplitude. As the frequency increases, amplitude will also increase, and as the frequency decreases, amplitude will also decrease. So you can see the sinusoidal waveform that we have shown on the vertical axis side, on the output side, is nothing but variations in the amplitude. So this were the variations in or changes in frequency, and what we have got here is nothing but variations in amplitude. So this explains a very simple conversion of FM to AM. So we have obtained this by using a very simple structure of transformer and the bandpass filter on the secondary side. In practice, both these capacitors are variable just to make sure that any FM signal at any variable carrier frequency can enter into the circuit. The bandpass filter on the primary side is to make sure that no unwanted frequencies will enter into the circuit. The frequencies that enter into the circuit are between Fc minus del F to Fc plus del F, but that's again the instantaneous frequency. In other words, the desired frequencies in the range of bandwidth of the FM signal should enter into the circuit. So anything outside the bandwidth of FM signal should be removed, and that's the job of the input bandpass filter. But the bandpass filter on the secondary side, which is the output bandpass filter, will do this whole operation that we have just now discussed. So it will convert FM signal into the AM signal, and for that to be possible, we must center the secondary bandpass filter at a frequency FR which has to be greater than Fc plus delta F. So the entire input frequency range will fall on the lower side of the frequency spectrum. And this is simply done so that low frequency results into low amplitude, high frequency results into high amplitude. If we take it on the other side, the right hand side of the frequency spectrum, then low frequency will result into high amplitude and high frequency will result into low amplitude. We don't want that. We want direct proportion between variations in amplitude and variation in frequency. The circuit is called single slope detector simply because we are using only one side or one slope of the frequency spectrum. So it is called single slope detector. Sometimes it's also called single tuned detector because we are using one bandpass filter, one tuning, and converting FM signal into the AM signal. The drawback, the very obvious drawback of this detector is the non-linearity. The single slope that we are using is highly non-linear, and that means the conversion that we are obtaining from FM to AM is non-linear. It is not linear conversion, and hence the distortion in the output signal is very large. So we need something in which this non-linearity can be reduced and the conversion from FM to AM can be made much more linear. Now for that we will go to the second FM demodulator, which will be called double slope detector, because in that case we will use, instead of using one bandpass filter or one tuning circuit, we will use two tuning circuits together, and with two tuning circuits will come into picture two different slopes, and the arrangement will be such that two non-linear slopes will be used to convert it into more linear equivalent slope. So this can be done by simply having a subtraction operation between the two. If you subtract the two non-linear functions, then all the alternate non-linear powers will get cancelled, and hence the linearity will improve of the overall function. So let's now discuss the second circuit, which is double slope detector.